Ladies and gentlemen, we are recording. So, first things first, as far as today is concerned, something to write with. Newton's third law slides that I believe I gave to you yesterday, but we didn't actually get to. So we'll get to those today. Our plan for today, first we're going to go over Newton's third law. That should take 20 minutes, 25 minutes. So with the remainder of our time, we'll watch the Magic School Bus, use it as our review activity for your test scheduled for tomorrow. Okay? Calendar-wise, right? There's your test. I talked to you a little bit about the test yesterday. 25 points. It's 23 multiple choice questions and one short answer question. I can't tell you what it is. You know, so.
Is it like a math problem?
No, it's not a math problem. At the beginning of class today, I gave you guys back the quiz you turned into me yesterday. Quiz questions obviously are a good place to start when you're studying, right? Similar questions things that end up on the quiz have a good chance of ending up on the test. Okay, so make sure you're looking over some. So Sam, as far as the math part goes, right? There were a couple of multiple choice questions in there that were real simple. That's what the test would be like.
Right,
yeah,
but like last test, they're like those 31.
Yeah.
Like that. Okay.
Yeah.
I have a question about number 6.
Okay, number 6. Go.
Yeah, because I kind of figured it out. Just like I don't really know how I got it, but I got it right. And it's like the same girl pulls the.
Okay. So.
Would you do 20 minus 10 divided by 5?
Because the net force takes into account all of those forces. But if there's a frictional force in there, yeah, number 6 on the quiz being the calculate the acceleration. Right?
Yeah, that's what I thought.
In number 6, there was only one force. So when we talk about the net force, if there's only one force, that's the net force, right? But if there's 2, we have to take into account which direction they go and stuff like that. Okay. And then number 9, what I'll probably do is I'll probably make the test out of our quiz out of 10. Yeah.
Is this instead of law?
Yes.
So I have a question on the
Yeah, I'm going
What?
ahead.
I'm nice. So anytime something moves, like inside something, like with the pencil example in the bus, it will stay in the same place, just the bus is moving.
Right, because if they're two, Alex, for number 9, okay, the question with the bubble inside the level. If they're two separate objects, and a bubble is an object, it's made of mass. It's not a lot of mass, it's a gas, but it has mass, but has inertia. If those two objects are separate from one another, they will each experience their own inertia. So whatever happens around them doesn't necessarily affect them. Right? Example I gave later in the day yesterday. Have you ever been in a car and you try to drink something and like your mom or whoever's driving the car steps up, well, either way, stepping on the gas is always the one that makes me angry, right? But if you're drinking something and somebody steps on the gas, what happens to the water? It falls into your face, okay? Not because the water is falling into your face, right? The water has its own inertia. It just stays in the same spot. But what are you doing? You're moving forward at a faster rate than it's moving forward. So that's why it looks like it's going backward. But
No, not the water, you.
No. If somebody hits the gas,
Yeah.
no, somebody hits the gas, you move forward.
Because
You're sitting on the seat, right? I suppose at the beginning there might be a little bit, but once you hit the seat, right, you're moving forward with the car, but the water in the bottle is staying in the same spot. So it looks like it feels like it's moving backwards at you. It's really not you. It's not the water moving backwards. It's you moving forward.
Basically, any example, it's just gonna be like that.
Pretty much. Yeah. You ever been on a school bus before and somebody drops something on the floor and it rolls all the way back to the back?
Yeah.
It's not really rolling to the back. I mean, it is kind of eventually, but at the beginning when the bus starts moving,
it's just at the same
it's staying in the same spot. The bus is moving underneath it, and that causes it to look like it's going
like
back.
a perfect example, right?
Because everybody's experienced it before. Anthony, go ahead.
So if a bird is standing in midair in 24 hours, would it travel the world?
Technically, I suppose, yeah, because it's staying in the same spot. Now, the one thing there is that it would have to have the wind keeping it, from moving forward, basically. It would have a constant wind. You know what I'm saying? Because if it starts flying, it's going to continue moving forward with its inertia, right? But if it's flying and there's a wind in its face that's the same strength as it's flying forward, then it won't go anywhere. Does that make sense? Because the forces on it are balanced, but the Earth would still be turning underneath it, I suppose technically it would be possible. Sure. Parker, go ahead.
About the bubble problem.
Yeah.
The bubble, I think, isn't really a thing. It's where the water isn't.
The bubble is a thing. It's made of gas, and gas has mass.
I don't even know what that thing was that they're.
The liquid has more mass than
Sure.
the bubble.
Sure.
So it would move back.
But
and
it's
force the bubble.
but no.
Yeah.
So the bubble has its own inertia, and so it stays. It should stay where it is. Yeah. Well, see, I just wanted to show you
Yeah, because
what
like
it
I've
is.
seen one of those, but that bubble right
Yeah,
there.
that bubble right there.
So then if it. That's cool.
So, but because of the thickness of the liquid, sometimes it doesn't work exactly the way it's supposed
Thing is,
to.
it's like-
Because there may actually be some other forces that are acting on it. So, here, go ahead.
So is C or A right?
Technically, I would like C to be the right answer. Okay? If we talk about it in terms of inertia under ideal conditions, C would be the right answer. That it stays where it is, but it looks like it's going backwards because everything's moving forward underneath it. Okay? Easy back there. Settle down. All right, good.
Yeah, so with the,
Yeah.
does that mean the pencil is staying at the exact same place, so wouldn't it have to be going as fast?
Now, in the pencil and the bus example that we did in class, okay, what is the pencil already doing because you're holding it,
Oh, it's already going to.
it's already going forward, so it keeps going forward with the bus. Now, if you let it go, and if you were at a stoplight, you let it go, and then the bus started traveling while it was falling to the ground, it would look like it landed behind you, but really, you've gone forward and it just landed in the same spot that it was in. Does that make sense? But if it was already moving, it lands next to you because it's already moving, and so your inertia and its inertia keep it going forward. Okay, good.
What about? I don't really know if this would like be the same, but what if you like threw something out of your car, you know, like a piece of gum or something, and it flies back? Is that just piece of
That more has to do with wind resistance, that now it has another force on it that's causing another acceleration, not backward acceleration. All right, we good there? Okay. Let's wrap it up here with our last topic, and that being Newton's third law. Okay?
Oh, was that just up there?
Oh, did we not finish?
We just
Oh.
like stupid food.
Check.
No,
So,
wait,
uh,
it.
So,
Oh, okay.
to wrap up
Oh,
what
yeah,
we did
no, we did.
yesterday,
It's fine. I got it.
did you finish the last two?
Yeah.
Okay. Basically what it comes down to in the last two is that sliding friction only acts on things that are still moving. And once things stop moving, friction stops acting on them. So, for example, okay, if we take our book example, okay, that book moves forward. And we talked about the idea that once I let it go, there's no force pushing it forward anymore. And the only force acting on it is coming from friction in the opposite direction. It keeps moving forward because of its inertia. The opposite friction force slows it down until it stops. But once it stops, that friction force can't be there anymore. Because if the friction force was pointing towards the front of the room as it was slowing down, once it stopped, that friction force was still pointing towards the front of the room. What would start happening to that book? It would start coming towards the front of the room again, and that doesn't happen. So the very first thing that we wrote down about friction is that friction has to oppose something, right? Static friction opposes some applied force. Kinetic friction opposes motion. If there's no motion, there's no kinetic friction. If there's no applied force, there's no static friction. So that book, as it sits there still on the ground, is not experiencing any frictional forces because there's nothing for friction to oppose. So the last two things in your outline. Number two, sliding or kinetic friction only acts on objects that are in motion. And then if there's no motion, there's no kinetic friction. Yeah, so So sliding friction only acts on object when they're moving. There's no motion, there's no kinetic friction. Good there?
Yeah.
All right. Let's do Newton's third law. Okay. From a pure rote memorization standpoint, we good with rote memorization?
No.
That just means you memorize something and don't really like your
Like
math,
you don't know what it is.
like your math facts, like 3 + 4. You just in second grade, you just have to memorize that's 7. I mean, you could count, but really you just or if you just memorize something and recite it, that's like a rote memorization. Okay? From 3 + 4 is 7.
I thought you said 2 times 4.
No.
Well, you didn't memorize them right.
No, I guess. Apparently my road memorization
Yeah.
is not effective. So, Newton's third law. Newton's third law you've probably all said before, you've probably all heard before, okay? If we review, Newton's first law. Newton's first law gets summed up with one word, right? What is that one word?
Inertia.
Inertia, right? And we said that Newton's first law deals with things staying the same, not changing what they're doing. Newton's second law can get summed up in one word as well. What is that one word? Not force. What did we say Newton's second law deals with?
Oh, it's
Newton's second law deals with acceleration. It deals with things changing. But this mathematical formula shows how force and mass are related to the acceleration of that object, how they can affect how much acceleration there is. So Newton's second law is acceleration, or F equals ma. Okay? Newton's third law deals with what happens when things interact with one another. What happens when these things come into contact with one another or apply forces to one another? And you've heard it before as, for every action, there is an equal and opposite reaction. Okay? But as far as more descriptive, as far as what's going on, Newton's third law gets summarized this way. When one object exerts a force on the second object, that second object will exert a force back on the first that is equal in magnitude but opposite in direction. We summarize that idea with the idea of action-reaction. That if I apply a force to something, it automatically and without trying applies a force back on me that is equal in magnitude but opposite in direction. Okay? We refer to those forces as action-reaction forces or action-reaction pairs. These equal and opposite forces we refer to as action-reaction forces. And action-reaction forces are equal in magnitude, but opposite in direction. Okay, you got the basics down? Now, I really, really, really hope some of you are sitting there thinking to yourself, something's wrong with this. Okay? Is anybody thinking that to themselves, that there's something wrong with this law? What's wrong with this law?
No, I was just wondering. So, okay, never mind.
Go ahead.
If they're equal in magnitude, nothing should happen.
If two forces are equal in magnitude but opposite in direction, what is that? That force is 0. That's equilibrium, right? And if that's the case, what would never happen, ever? Nothing would ever happen. No acceleration would ever occur. So is this just like a throw-in? Like the other two laws were really good, so we just keep this one around just because, the first two were good, but, okay?
Is it because the opposite forces, when it doesn't move, is acting on the same thing, but this is acting on a move?
Good. All right. So here's striped girl, here's blue girl. Okay? If you notice the beginning of the thing, it says striped girl, stop pushing me, and the blue girl says, no, you stop pushing me, or whatever it says. So,
It's like how decked out in gear they are for
Hey.
rollerblading. Like,
safety first.
yeah, I know, but
Safety first.
yeah, I broke my ankle.
Oh, this coming from somebody who got hurt while rollerblading. So, all right. So striped girl pushes on blue girl. There it is. Okay? But Newton's third law says that equally and automatically, without trying, blue girl applies a force back on striped girl that is equal in magnitude but opposite in direction. Automatically and without trying, that happens. She doesn't have to turn around and push striped girl. Whenever blue or striped girl applies a force to blue girl automatically applies that force back to striped girl.
I know, yeah, like this.
Okay. So I mean, if you've ever been ice skating before or something like that, you can see this happen, right? Right.
So like, push someone. I would agree.
Not necessarily, because hold on to that for just a second. Okay. Here, if we're just talking about these action-reaction forces, okay? We're not concerning ourselves with anything else. All we're concerning ourselves with is what striped girl is doing to blue girl and what blue girl is doing to striped girl. Okay? So, Anthony, go ahead.
Is this like how dominant works?
Not necessarily. No, that's more one goes to the next. There's something going on there, but that's not exactly like this situation.
Is it like a rebound effect almost?
Kind of like a rebound effect, yeah. Okay. So Parker. Okay. If we look exclusively at blue girl, okay, does blue girl have a force on her? Yes. Is that force on blue girl balanced out by anything else? No. So what's going to happen to blue girl in this situation because of this force? She's going to start accelerating. In which direction? Towards the right. Okay? If we look exclusively at striped girl, okay? Easy. If we look exclusively at striped girl, is there a force on her? Is it balanced by anything? It is not. What will start happening to striped girl because of this force?
Go back.
She will start accelerating to the left. Parker.
Where's the force on her?
No, if they're just standing still. Okay. Yeah. We're just standing still, striped girl pushes on blue girl. Okay. Parker. We said, are these forces equal in magnitude and opposite in direction? Yes. Okay. Don't cancel each other out because
It's acting on two different objects.
these are two different objects. Okay. When we talk about the net force, we talk about the combined effect of more than one force on an object. But these are two separate objects. Those forces can't cancel each other out because they're not on the same object. Are they equal in magnitude? Yes. Are they opposite in direction? Yes. But they don't cancel because they don't act on the same thing. Okay? Which means the end result being that both girls end up moving, but in opposite directions. Very cautiously, as you can see. Okay? Especially blue girl. She's not too sure about this whole situation here. Okay? So, both girls end up moving, but in opposite directions. Now, Miriam, your argument to that kind of being, right? Well, I can go and I push these books. I didn't fly backwards, right? Okay. Now, let's talk about. Yes, so Chris, you said because of what? Different masses. Now, that is true, but we talked about the idea yesterday with friction that the mass of an object doesn't determine if it starts moving or if it accelerates. It determines how much it accelerates, but not if it accelerates. So even in this case, if I push this pile of books that has a lower mass than me, Newton's third law is saying those books are applying a force to me. And if I feel an unbalanced force, I should start accelerating. Will I accelerate as much as those books? No, because my mass is bigger. But are those books the only force that's being applied to me when I push on them? No.
Friction.
Right? You'll never get to see that on video, so that was like an exclusive in-class only right there, okay? But there, static friction between my feet and the floor balances out the push of the books on me So I don't move. Not because the books don't push me, but because I'm balanced out. The reaction from the books is balanced out by the friction of my feet. Those two objects, those two forces act on the same object. They can cancel each other out. Does that make sense? Okay. Chris, go ahead.
So does this still apply, say, like, if you have a smaller person that's a bigger person?
Yes.
And, like, they run at each other, the bigger person doesn't move, but the little person falls out?
Yes.
If they're the same.
Pierce, so that was actually we could say at the end. That's okay. We can do it now. Okay. Yeah. If we have people playing football, all right. One guy's running one way, one guy's running the other way. Big guy, little guy. Okay. They run into each other. Okay. It looks like little guy could just get plowed over, and big guy just kind of whatever goes right through it. If we looked at the forces that each of them experience, Newton's third law says they experience exactly the same force. But their motion, their acceleration, isn't exclusively determined by the force. It's also determined by what? Their mass or their inertia, right? So a little guy is going to experience more acceleration, not because he experiences more force, but because his mass is smaller, so his acceleration is larger. Does that make sense? Okay. So yeah, when we have collisions, any kind of collision, those objects experience the same exact forces, but what happens to them because of those forces is a result of their mass as well. So it's not just how much force they do. Okay. Good there? Okay. Let's wrap this up with a comic strip. Okay. And you have the comic strip on the back of your notes there. So this comic strip starts with this. Okay. Farmer tells the horse, "Hey, giddy up. Pull this cart so we can get going." And the horse says, okay, let's get past the fact that it's a talking horse, right? Okay. The horse says, "No can do, my friend. For me to pull this cart would be a futile effort." Are we good with futile effort?
No.
Basically, it's not even worth trying. Okay, you're not going to win, so you might as well not even try. That's it. That's a good attitude, huh? Like, well, it's not going to work, so I'm not even going to try. But anyway, the horse then proceeds and says, "You see, if I pull on the cart pulls back on me. By Newton's third law, those forces are equal and opposite. They'll cancel each other out. A zero net force won't get us moving." So, right, the horse is in the same boat a lot of you were in 5 minutes ago, 10 minutes ago, or whatever it was, right? So, if we look individually at those objects, there's the horse, there's the cart. What the horse is saying is that if I pull on the cart, what automatically has to happen? Cart pulls on me, just like that. So the horse's argument being, well, that's zero net force and it won't get us going. But Parker, we've already established the fact that those forces won't cancel each other out because
They're
two separate objects. Now, the horse could make another case in this problem. If we look at this in isolation, just those forces, what would happen in this case? What would be the end result of this situation as drawn up on the board? Dummy.
the horse runs.
Where? Somewhere in the middle between where they started. Okay? Because the cart is experiencing unbalanced force to the right. What will it start doing? The cart is experiencing an unbalanced force to the right. So what will it start doing? It will start accelerating towards the right. The horse is experiencing an unbalanced force to the left. So it will start accelerating to the left. Pierce, will they meet in the middle? Not necessarily. What would determine if they meet in the middle? They would have to be equal mass, okay? If they were equal mass, that means they would experience the same acceleration, and then they would meet in the middle. We can't really say for sure whether these two things are equal mass, so it's kind of hard for us to tell at this point in time, okay? But they will meet somewhere in the middle if we look at this in isolation. Okay? But the important thing being, is the horse right? Will these forces cancel? They will not. But if we look at what really happens in this situation, the cart is going to move to the right because of that force that it's experiencing. That's okay. That's what the cart does. But what does the horse do as well? It moves, well, in real life, which way does the horse move? It moves to the right as well. That means there has to be another force on this horse, right? Okay. And which way does that force have to go? It has to go to the right, and it has to be how big compared to the blue force? It's got to be bigger, okay? There's another object that enters into this situation. Not gravity. That Earth, not to scale, okay? So, let's talk, before we talk about walking, let's talk about jumping. If I want to jump into the air, what do I do first? You squat down, right? And then, what do you do after you squat down? I push. I push where? Down. I apply a force to what? To the ground. What does the ground automatically do to me? Apply a force back. Which way? Upward. The harder I push on the ground, the harder it pushes on me. Right? If you want to jump higher, right, you make your legs stronger. Why? Because now I can push on the ground harder. Okay? But, if I push on the ground, and the ground pushes on me, I start accelerating because, well, how hard actually would I have to push on the ground in order to jump upwards? Not my body weight. My body weight is actually the force of gravity acting on me, right? Okay? I would actually have to push on the ground more than my body weight. Because if I push exactly the same as my body weight, Nick, what's the net force on me? Zero, and I don't go anywhere.
Like, is that just like you're standing?
Yeah,
You're
pretty much.
pushing.
Pretty much, yeah. Okay? So if I push on the ground harder than my body weight, or harder than gravity is pulling on me, now I experience a net force upwards, I start going upward. But, on the other end, have I applied a force to the Earth? Yes. Is there anything on the other side of the Earth balancing out my force?
No.
Let's say in isolation. No. Is there another physics teacher in China right now who's doing this lecture? And possibly. Okay.
Most likely not.
Maybe not. I mean, it's like 10 o'clock at night in China, which means they probably have like 2 more hours of school left.
Yeah, exactly.
But, you know. So anyway, but I'm applying a force to the ground. It applies a force to me, but there's nothing to balance out that extra force on the Earth. So does the Earth start moving backwards?
Kind of, but its mass is
No.
Does the Earth start moving backwards? Yes. But what's the Earth's mass? Really, really big. So how much acceleration does the Earth experience?
Like that much.
Like this much, right? Can I move the Earth? Yeah, watch. Okay.
Felt it.
You know, whatever I do, whatever
in the world.
Now, wait. So first, as far as my jump goes, whenever I jump in class, I always do that. But it always reminds me of Anchorman. Like, ever see Anchorman?
I
Anybody?
just watched that.
When they go buy new suits. When they get on. So anyway, you've never seen Anchorman.
Wait, can we all like move it? What if everybody in the world jumps?
So the questions that come up. There's 2 questions that need to come up. First, okay. Well, let's go first with Sam's question. Okay, if everybody in the world jumps at the same time, okay, that wouldn't anything happen because I'm over here jumping, right, and then somebody in Africa is jumping as well.
Let's say everybody in the United States, everybody just came to the United States and jumped.
We could have a big house party here in the US of A, right? There'll be a party in the USA,
Yeah.
and if everybody came here and we all jumped at the same time.
Would the Earth go like flying, or would it just move like?
Answer being I don't really know because I've never done the calculation
We
before.
totally should.
So, Parker, you bring up another good point, right? What if we all walk in the opposite direction that the Earth is spinning? Could we stop the Earth from spinning? Is that where you were going with that? Yeah. The answer is probably not. But I've never done the calculation before, so I don't know. Okay. Donna, good.
Actually, one time in Britain, a whole bunch, I think it was 12,000 or 120,000 school kids all jumped at the same time to see if they could start an earthquake.
Really?
And they did.
Well, maybe we
Drat. Yes.
It's like okay, like the Chuck Norris fact where he does the push-up and he pushes the.
Exactly. I mean, Chuck Norris is basically just working Newton's third law, right? So, yeah, he's so dense and muscular though that the effect of acceleration is.
Are you
All
going
right.
to school us out?
So, the end result of this.
What is happening?
The end result of this being, okay, in order for the horse to move forward, he has to push on the ground harder than the cart is pulling back on him. So if there's a net force in the other direction, he starts moving forward along with the cart. Okay? Every time you take a step, you apply a force to the ground. It applies a force back to you. Technically, the Earth experiences some acceleration because of that unbalanced force that you have applied to it. But the Earth's mass is so large that the acceleration is so small that, yeah, exactly. Yeah. We're talking like 10 to the minus 24th power acceleration. Okay, so don't worry about it. Yeah.
The real
So saying, like, no matter what, like, how bigger, like, the other thing is, like, it still moves a little bit since it's so much bigger, like,
Yes, because they still experience the same force, right? Now, as long as we can talk about it in isolation, right? If just those two forces. Like, remember Pearson, like, I push the book, okay? I don't move, but not because the book doesn't push back on me or not because I'm so much bigger than the books. I don't move because there's another force acting on me that's canceling out the book's force. Okay? If we talk about just me and the books, yeah, I move because of me pushing the book. Not as fast as those books, but I would still accelerate because of that. Okay? Anthony, go ahead.
For like the Earth and like it only moves a little bit, wouldn't like those little bits add up?
Because if you look at it, every time you walk here, if somebody on the other side of the Earth is walking as well, those forces are canceling each other out. So yeah, don't.
China and the super overpopulation.
Don't worry. It'll be okay.
What if we all just
So,
look through this?
To end this off, the farmer taunts the horse a little bit and says, "Hey, just push backward on the ground, and by Newton's third law, the ground will push equally on you. Then I will just simply follow along." So the farmer then taunts him and says, "Hey, this ground is doing a great job because really it's the ground that's pushing forward, right?" You know. So. And then the horse replies with "Physics grumble physics," which I'm sure many of you have experienced sometime over the past like month or so.
Yeah, I saw a horse.
No, you specifically.
I
grumble.
grappled.
So yes, sir.
But with the ground, if you just push on the ground, wouldn't it make the horse, wouldn't it make the horse go up?
Yes. When you walk, you're technically not pushing down. You're actually pushing back. Yeah, you're pushing. Yes. Yeah.
Because then every step we would take would be like a jump box.
Yeah. So there are about 5 minutes. We can watch some parts. Okay. What I'm going to do for you here. There's a part at the beginning. Okay. They're playing baseball outside, and Dorothy Ann. I don't know if you guys remember the characters or not. I know the characters because my son watches Magic School Bus. So anyway. Not because I make it. He really dislike it. Actually.
You're gonna be so lucky to have like.
So. Dorothy Ann she's like the smart nerdy girl, and they're playing baseball, and Ralphie she's reading a book about physics, and Ralphie uses her book as home plate and blah blah blah. But they end up actually going into the book to play baseball on a frictionless surface. So
That'd be fun.
okay.
This is crazy.
Is that possible?
No, because we can't get rid of friction. So. Oh, I don't want you to
Hey, yeah.
So.
Well, I
DLC.
guess
Oh,
It's
this
not
is
good,
DLC.
those frictionless ramps.
Yes.
I know.
It's Ralphie the runaway football. Yeah, there's no stopping it now. Library and yes, let's go.
Please! Page 97. It's the page I was talking about. It's all about a world without friction. It looks like the world of baseball to me. Come on! Ralphie, watch out! The ground on that field has no...
Why is it so light?
Yeah, I think that's I'm gonna try and fix it. Oh, I know why. Because I'm recording. Still. So.
If